Why do we say that free energy? Why do we use the word free? Free can be kind of a deceiving word, and it's not because it's free as in there's no cost. The word free in this case means available. And so free energy, it's the maximum amount of energy that is available to do work. And many exothermic reactions, that heat that is released goes into increasing the entropy of the surroundings. And so it is not available to do work. And so really, delta G is a theoretical limit as to the amount of work that can be done by a chemical reaction, because we do lose some of that energy as to heat up the surroundings of the chemical reaction. So free really means available. It's a theoretically available limit. In real chemical reactions, quite a lot of the energy is lost as heat. So here's an example where we have 100 watts of energy coming into our light bulb, but most of that energy, 95% of that energy, is lost as heat. Only 5 watts is being emitted as light. So that means that real chemical reactions and real processes are irreversible because we cannot get that heat energy back. We saw briefly that delta G and the equilibrium constant are related. So delta G is equal to 0 at equilibrium, meaning that the reaction is not it's not spontaneous in either direction. And we have a relationship that says delta G is equal to negative RT, R being the ideal gas constant, T being temperature in Kelvin, times the natural log of the equilibrium constant. And so if we look at the signs of our equation here, if our equilibrium constant is very small, less than 1, that means that our delta G is going to be positive. And so that means that the reverse reaction is going to happen. It's going to want to move towards the reactants. When the equilibrium constant is much larger than 1, delta G is negative, and that means that the reaction is spontaneous in the forward direction. And when the equilibrium constant is equal to 1, delta G is 0, and we are at equilibrium. Now, this is not new information. We already have looked at this when we looked at equilibrium constants and deciding which way a chemical reaction will go. This is just understanding it in terms of spontaneity and delta G. So if we have a small equilibrium constant, we are going to shift the reaction towards equilibrium in the reverse direction until we reach equilibrium. If we have an equilibrium constant that's very large, we're going to shift towards the products until we reach equilibrium. And if we're at equilibrium, then our delta G is equal to 0. Now there is a temperature dependence when it comes to the equilibrium constant. And the reason for this is because we have looked at free energy in terms of entropy and enthalpy. We have looked at free energy and how it relates to our equilibrium constant. Now, if we set these two reactions or these two equations equal to each other and rearrange them, we end up with a new equation. This equation can be looked at in the form of a line, where y is the natural log of k, m is our enthalpy, negative enthalpy over the ideal gas constant. Our x value is 1 over the temperature in Kelvin, and our intercept is the entropy over the ideal gas constant. Now this is very helpful for chemical reactions if we want to gain information about delta H or our delta S. And so this works over a very small temperature range, but it does give us lots of information about our thermodynamics.